All right, so the notes for this start on page 113. And I want to talk about the second fundamental theorem of calculus. You know, in class today, we talked about the first fundamental theorem. And the second fundamental theorem is sort of just like a corollary, things that maybe you kind of already know, but it just sort of formalizes it. And so, kind of look here, kind of our standard opening. You have a continuous function, on this particular interval. And like any point that's in that interval, if you are looking at the area under the curve at any point within that interval, and then you take its basically its derivative, look what happens. Like they cancel. It just verifies that a derivative and an antiderivative are inverse functions. But there are a few subtle things that the AP exam wants to make sure you understand what's happening. First is that whatever this variable is up here, kind of like when we had the accumulation function, that variable it has to be distinguishable and different from that variable. And so, and then whatever that upper variable is, kind of thinking about that as an accumulation function, when you do the derivative, it has to be with respect to that particular variable. But the inner function, like I said, is with some other variable, so its antiderivative symbol is there. But now look what happens. Your core function, the family of functions, stays the same. It's just that your f of t becomes f of x. So you do a change of variable. And I'll kind of show that here, that example. But really, that's all that's happening. The actual function itself remains the same. You just have to have a little bit of a difference between what variable are you integrating and which variable are you differentiating. Okay, so for that first example, it's defining g as an accumulation function, right? So notice that g of x is defined by that x there, starting at 3, and going up to that variable x. And now it says find the derivative of g. So finding the derivative of g, since g is an accumulation function, the derivative of g is basically going to undo the antiderivative symbol. So it's like squaring a square root, right? If you square a square root, like the square and the square root cancel, and you just have whatever is left over. So which would be underneath that value? So 3. So same thing here. The antiderivative and the derivative cancel, and you just get 3 times that thing squared minus 2. And the thing is that it is a change of variable. So because our g was in terms of x, our derivative will also be in terms of x. So if you want to write that cleaner, it could be like 3x squared minus 2. And you might say, well, wait a minute. What about like a plus c? Like we're so used to adding plus c for our constant. Well, a plus c would have happened if you integrated this, right? So if we would have integrated this, we would have gotten like a t cubed minus 2t plus c. And then when we do that derivative, notice the derivative cancels. Like the c would cancel. This would be 3t squared minus 2. But then we'll have to evaluate that, at x. And so that's why our t became an x. So when you see a derivative of an antiderivative, I want us to realize that those are inverses of each other. And it doesn't matter where that lower bound starts, because when you take its derivative, it would have been a constant anyway, and that goes away because the derivative of a constant is 0. Same thing here. We have f of t this time, and notice the t is up there, so that's okay. Which now this interior function is in terms of x, which is fine. It just has to be different than what our accumulation function is defined to be. So finding the derivative of f, since f is an accumulation function, it's going to knock out the antiderivative sign, and you're just going to get 4 times something cubed minus 8 times that something. And since f is in terms of t, so will our derivative be in terms of t. Okay. And when you get rid of the antiderivative because you're taking the derivative, notice that that would go away too. Both of those symbols together tell you that you're doing the antiderivative. Okay. Now, example 3 is more of like a command form, right? Like this says, take the derivative of an antiderivative. So they will cancel. They are inverse functions. And again, notice you're taking the derivative of something in terms of x, but then that ends up measuring area under something that was in terms of y, which is fine. So that has to be, if you think about, like just like we did the first two, it's the outside variable that will become the new variable of your expression. So the derivative of the antiderivative cancel, and you're just left with the interior function as a change of variable. So hopefully that's okay. You just derivative of an antiderivative, and you just do the change of variable. Now, there's a couple variations that you should be careful of, and maybe like you kind of maybe are already anticipating that, right? So like for here, notice that I'm accumulating starting from x to 3 as opposed to 3 to x. So when we think about our bounds being backwards, it's just like we're finding area backwards. Like that idea of going backwards represents a negative, a negative quantity. So the same thing's going to happen here. So like instead of saying, okay, well, I know this is x and this is x, and the function's measuring is under t with respect to t. So I know I'm going to do change of variable. When I find the derivative f prime, I know that it's still going to be a change of variable. So 3x squared minus 8x plus 5. But because my bound is backwards, right? My variable's down here, that changes my antiderivative, or the derivative of the antiderivative, so that it becomes, I'll use blue here, it becomes negative. So it's the opposite of that. And you could simplify if you want to distribute that negative, certainly do that. So there's your derivative expression. And, again, you might be thinking, well, why? Why is it negative? Well, according to the fundamental theorem of calculus, when we do like f of b minus f of a to evaluate that integral, and then so like we'd be putting the 3 in here, it'd be some constant value, the x there, it's some variable in terms of x, and then I'd be doing the derivative of this. Well, f of 3 is a constant, so its derivative is 0. And then you'd have an expression here. Its derivative would represent the function that you just took the antiderivative of. But because it's f of b minus f of a, that's why we have that extra negative. So in case you were wondering. Okay, so I guess the variation rule here is, when your bounds are backwards, multiply by a negative. I mean, just like we've been seeing. When bounds are backwards, multiply by a negative 1. Multiply by negative 1. Okay. Now, the second variation that we have here is if the bounds are the right way, but now all of a sudden you're putting more than just an x. You're putting a function within a function, right? So it still has to be in terms of this variable out here. So f of x will be the antiderivative from 1 to x squared of this particular function in terms of t. So the nature of this is like if I do the derivative of an antiderivative, it's still going to cancel that antiderivative. So I'm still going to think about it in terms of x, and I'm still going to get 3 times something squared plus 2 times that something. And, we kind of maybe did this without even thinking about it, but we just sort of inserted that variable. Okay, so we're doing the same thing. We're inserting that variable, but this variable is x squared. So because you're substituting something that's more than just an x, right? So if you think about that, well, then you'd have to ultimately multiply by its derivative, right? Hopefully you see a chain rule here, which is 2x. So it's like you're substituting the derivative of this and into you're substituting that function in, and therefore you also have to multiply by its derivative, as the chain rule. And so think about that. So you get 3 and then x squared squared, so that's x to the 4th. Plus 2x squared, all times 2x. And you could distribute that 2 here. So 3 times 2 is 6, x to the 5th, plus 2 times 2 is 4, x cubed. So there is your derivative with a chain rule. Okay, so then I guess I would say for that variation, I would say so the variation use a chain rule when upper bound is a function other than just x. And honestly, I should just say always use the chain rule, because like that way, even if it's an x, the derivative of x is 1, so it's not like you're going to be wrong, right? So use a chain rule when upper bound is a function other than just x. Okay, so what I want to do, and then I think I'll break this up into one more video. I want to look at the last variation. What happens if they are both variables, right? And look at that, and then I want to actually do a couple practice problems just to make sure that like that it makes sense to you. Okay, so let me pause this video, and then if you want to revisit it, go back, look at it. That's awesome, and see if you have any questions.